video is about molality and mole fractions. So we have molality and mole fractions are two ways to express concentrations of solution. We have molality, which is abbreviated as a lowercase italicized m. This is going to be your moles of solute per kilogram of solvent. One thing to remember is that 1,000 grams is equal to 1 kilogram, that K being kilo, so a kilogram. So what about an example of this? So an example would be, what is this should be molality of a solution that has 29.3 grams of sodium chloride dissolved in 1 kilogram of water. So this is similar to molarity, just using different units, so looking at a different type of relationship. So in our problem, we're given the mass of our solute to be 29.3 grams, and we're given the mass of our solvent to be 1 kilogram. Now we need to have moles of solute, so I need to change my mass of sodium chloride to moles of sodium chloride using my molar mass, and I get 0.5 moles of sodium chloride. Now I take my moles of solute, my sodium chloride, divided by my kilograms of solvent, so my kilograms of water, and I have 0.5 moles sodium chloride divided by 1 kilogram of water. 0.5 divided by 1 gives me a molality of 0.5 moles per kilogram, or I can write 0.5 molals, just like I could write 0.5 molar before when I was looking at molarity. Alright, you're going to try a practice problem now. This is not written in your notes as of yet, so I have it written on the board. Your practice problem, you want to calculate how many grams of potassium iodide must be dissolved in 500 grams of water to produce a 0.6 molal potassium iodide solution. Just remember, we can convert moles to grams via our molar mass, similar to before. When you're said and done, you should receive an answer of 49.8 grams of potassium iodide. Okay, mole fractions are another way to calculate concentration. Our mole fractions are going to be a ratio of moles of the solute or solvent to the total number of moles of the solute plus the solvent. So XA and XB are going to represent our mole fraction of our solute and the mole fraction of solvent. And then our NAs and NBs are going to represent our moles of our solute and our moles of our solvent. So depending on if you're looking for your solute or your solvent, you'll just rearrange accordingly. Again, they're fractions, which commonly like percents. It's the part divided by the whole. Okay? So your first example is you want to know what is the mole fraction of a solution of 1.25 moles of ethylene glycol in 4 moles of water. So we need to determine what's our solute and our solvent. Well, our solute is ethylene glycol because it's dissolved in our solvent, which is water. We need to label our variables. We have moles of ethylene glycol, just abbreviated EG, of 1.25 moles. Our moles of water is 4.0 moles. We set up our equations. Our mole fraction of ethylene glycol is going to be our moles of ethylene glycol divided by our moles of ethylene glycol plus our moles of water. We put in our number and units. 1.25 moles divided by 1.25 plus 4 moles gives me a mole fraction of 0.238. When I do it for water, I find my mole fraction of water is my moles of water divided by my moles of ethylene glycol plus my moles of water. So 4 moles of water divided by 1.25 moles of ethylene glycol plus 4 moles of water gives me a mole fraction of 0.762. Now you're going to try a practice problem. What is the mole fraction of 1 mole of sodium chloride in 500 grams of water? Remember, we're looking at moles here, so everything needs to be in moles, so we'll have to convert. After you do the problem, you should see that our mole fraction of sodium chloride is 0.035, and our mole fraction of water is 0.965.